Hello everyone, Namaste. I am Ramna who would like to present you the series on key learnings from chip development, part 3, which is on chip architecture. Some of you might know that chip architecture considers the requirements and the conditions to implement the functionality. That is why it is indeed the key executive vision of the chip. Thanks for learning along with me. Feel free to give suggestions. To get predictable, sustainable, and scalable system development, architecture need to be well planned and should be a well thought out process. It is actually a process of defining a collection of hardware and software components and their interfaces to establish the framework for the development of a computer system, like any system. So this is as defined by IEEE. To get some broad understanding, let us consider the architecture of a mobile system. Here, if you see, there are so many features of the mobile system, and these are typically sound, battery, display, Wi-Fi. This is all communication, and memory, security, camera, what type of CPUs are needed. All these things are different features, and these we have to collect all the system requirements, and we should also collect, aside to this one, the system constraints. That means, like, the dimensions of the mobile phone should not be more than so and so, like that. It should also perform at so and so gigahertz of frequency, and it should be consuming very less power. Similarly, thermal considerations, cost should not be too high, it should be less than, say, $300. And reliability and the technology is slightly debatable, but I am saying that if you need high performance and low power and all, you need to go to the latest technologies. So all these are all constraints. So to ensure that we meet the desired features, to implement these things, there are several possible architectures. Okay, so you already know that in the industry there are so many chips, mobile phones available, that reflects the clarity that architecture of these different mobile phones are different, and the CPU, GPU, what they take for implementation, those will be different, and the battery considerations, several items, how they need to be connected, how the data flow exists, those will be different. So by considering all these things, you can say that architecture differs from one mobile system to another. Here you will see different mobile system realizations, say from Samsung, iPhone, and Nokia, Oppo, and Google Pixel. So in all these realizations, the features are almost same. However, the functionalities, the constraints will differ. Definitely, that will play a major role. So you can understand that architectures are playing a major role in figuring out how the data flow should happen, how different components, like image components, sound components, and different battery, all these things, how they need to be connected, how much they need to be added, how much communication should happen between all these, what should be the frequency. All these things are controlled by the abstract level of determination of these items through architecture. And here, when we mean architecture in these big systems, we need to think that both hardware architecture and software architecture exists. However, we will further restrict ourselves to hardware architecture only. So, and one more point to mention here is like you know that in Samsung or Google Pixel or any other mobile phones, they will have several derivatives. So by having several derivatives, the advantage with that is based on the specific technology, based on the time frame, based on the available resources, they will be based on the roadmap. So they will be adding the features and by considering the different conditions into account. This is very good in terms of environment and sustainability, and it will not also pain the design community. Architecture of a system depends primarily on these items. One is functional requirements, that means like what features need to be achieved, and set of components which are available at that point of time based on the conditions of set or constraint set to realize the functionality. And it will also depend upon set of connectors which will help in coordination, communication and cooperation between several components being considered in realization of the system. So thus all these items are considered so that the system design will happen. And we will figure out how architecture plays a vital role in shaping the structure and behavior of the system. That is how, as mentioned earlier, different types of realization happen in the mobile phone system. So let us take Ford Mustang 1966 ignition system. So in this ignition system, if you see, there are the main function to be achieved is like uh, once this system is employed in a vehicle, when the ignition is initiated, the car should start. So our vehicle should start. So here, this is a typical component listing and how the connectors are connected. Okay, so if you see here, there is a battery and a rotor and spark plug and different accessories and all these items. Okay, relay coil. So if of all these things, the conditions will say how the connectors need to be connected. Okay, so all these things they will specify and conditions will determine, and how they need to be connected, this also matters. So architecture will tell like what type of components, same components, battery, based on the system space, that means like LWH, based on the system LWH, width and height requirements, space available, and what type of material should go in the battery, that means like sustainability. I am saying that in the current context I am talking. So what type of battery is it, lithium battery or sodium battery? So like the different components, how they will come, what type should be picked. So based on the socio-cultural requirements, all these items are considered, and based on the connectivity, based on how and when they need to be timed, so are triggered, so that the signal will move from one component to the another. So this is all part of the architecture. As already mentioned, architectural design plays a pivotal role in the translation of conceptual ideas into a meaningful design through creative synthesis of functional requirements while considering technical constraints, socio-cultural context in a sustainable manner. As such, each one of us is already doing systems level thinking to solve problems in our career and personal life. So remember that we are the architects of our life. Okay, so this process also involves looking at different parts of systems to understand their role in the system as a whole. So let us understand a bit more on systems level thinking. So in the systems level thinking, look for underlying systems in your life. Okay, there are so many sub parts. So all those sub parts, how they work and how they are connected together, and how the bigger picture needs to has a role in connecting various subparts, how the communication need to be taken care of. All these things we need to be aware of. So then we will be able to provide a holistic solution, even if there is something wrong in the problem at a different time frame, because we know about the entire system. So that is why we need to be aware that we are architects of our life, and we should make informed decision by knowing systems level thinking. As observed in the conventional ignition system, and as per our day-to-day life, how we are having systems level thinking, even in chip architecture and design also, we need to apply those principles to solve the different scenarios in the chip architecture. Here we will figure out what are the elements possible, and how the elements need to communicate with one another, and how the control unit should process the instructions, decode and all, and it needs to send to the processor element, and it should fetch the data from memory, and it should once it is sent to the processor element, how it the processor element will processor element here is a CPU or a GPU. So then how all these things communicate with one another, how the data comes from the IO unit. So all these things are part of the chip making. And in the chip architecture, or the chip architect will uh, understand what functions need to be implemented, and what are the resources he has, what are the design constraints, technology constraints, and based on that he will pick and then create these kind of uh, top level, abstract level uh, models, so that, and he will also give the timing diagrams where possible at a very high level. So that means like clock level. That is how he will implement different tasks and functions, so that the top level requirements will be translated into the next level. So in the same way, if you observe in the old 8051 microcontroller architecture also, here this is the IOs which is mentioned here. Okay, and here these are the memories units, this one here. Okay, so this one, and this is the CPU, this is the processor element. So, and this is the bus, same thing here. Okay, so various units will be moving. That means like here the data will be moving from memory to the IO, like this. Okay, and the processor elements and memory will communicate with one another, all these things. So, and please note, just like in our highway, when one assume that there is only one road which moves in which we have one road, so then we will use a contention. That means like when one data stream is passing, we will stop the other data stream, just like how we do in the normal day-to-day life, like using a traffic light system. Same thing we use it in the chip architecture also. And here we have some urgent calls we need to handle. We use interrupt controllers and all like that. The same items, see how we need to create one system, that those same systems we will be creating in the chip architecture. Same principles how we use in our day-to-day life, to large extent we use in the same fashion. As observed in the earlier 8051 system, which will take only single instruction and single data stream. Uh, Here you will observe that this it will control unit will take the one instruction from the instruction pool and then provide it to the processor by taking the one data point, and hence afterwards it will go to the next instruction. So this is called the SIST, single instruction single data stream. So the conventional Intel 8080, Intel 8086 and Motorola 6800, all these things were earlier using more or less SISD kind of architecture. Aside to this is one of the Flynn's taxonomy, where the different way of architectures of the systems are made. If you observe, there are many types of possible architectures exist to implement the same functionality. If you observe here, this SISD is represented in this way, and here multi-instruction single data stream is represented in this way. So here multiple instructions are taken, but however, if you observe, this is the data, same data is provided to both the processors. Coming to here, the single instruction and multi-data stream. So here, though the single instruction is given to the different processors, but there are the data what is provided to these processors are different. In this one, this is multi-instruction and multi-data stream, and this is the Intel 8080 processor example. Here this one is the multi-instruction single data stream, wherein the most of the time these are all made for the pipelined architectures, wherein the same data is taken and multiple instructions are provided to them, and the system is constructed for such a situation. And in this architecture, wherein single instruction is taken but multi data streams are evaluated. So this one will be generally be done in a GPU kind of architecture, wherein the each vector of it is more like a vector processing kind of thing. The data, multiple data is loaded into the processors, and then they will be same instruction will be executed. So if you observe here, for simple examples, this is a this will perform a function such as sin x. This is taken for a simplistic example, wherein x is the data and the operation to be performed is sin. Okay, so it need not be sin, it can be e to the power of x or log x, or it can be any other functionality. Okay, so here it is just performing only this one, then the instruction is just to perform sin x. And in this specific scenario, here the data stream is same, x is same. However, it is asked to, these two processors are asked to perform different instructions by providing different controls and instructions. So the each processor, assume the first processor is performing sin x and the second processor is performing cos x. In this specific scenario, the data streams are different. If you observe the data streams, multiple data, so data streams are different, x and y. However, the instruction is same. That means like they are all performing sin operation. So that is how this architecture will perform. This is mainly done in a GPU kind of application, and in this one, multiple computers will be performing with multiple data, multiple instructions will be performed. Sometimes what happens is you can consider that in the SIMD kind of scenarios, you can make it as a parallel one. So you are making one SIMD out of one path, and in another one there will be another SIMD. So here it will be used in a aircraft kind of scenario engine. So wherein they need to have a twin engine. That means like same instructions, same data. That means like multiple instructions, multiple data need to be going through identical pipelines, and they assume that one set of so pipeline is broken, they will immediately switch on the another pipeline. And this MIMD is a very complicated one to address different types of scenarios. So all these different types of architectures are needed to handle different requirements of the system, mainly to improve the efficiency and the throughput. Definitely the cost is also high. See, we can implement the MISD or SIMD kind of systems definitely with the SISD, but there is some cost penalty, there is some area penalty and throughput penalty. Architectural exploration deals with a suitable system architecture by distributing the system tasks in the specifications onto those identified components based on how they contribute to the overall functionality of the system. Aside to this, architectural trade-offs need to be taken based on the design metrics, specific thresholds, which will help in choosing the required IP, technology selection, and implementation strategy, to name a few. Actually, this is how whether it needs to be SISD or MISD, this kind of different schemes will evolve. And aside to that, we need to also know that since each component has a single control, we need to serialize the tasks in each component by understanding its own specific timing, priority, and communication pathway to handle data transfers. All this need to be well documented with suitable diagrams in plain language where possible. However, we also need to pay more attention onto the keywords and units which are used, and they should have standard meaning. Every requirement that potentially constrains an architecture or design decision must be questioned and clarity should be obtained, especially in facts or some other application notes. Note here that each expert in a complex system has visibility only up to certain extent. Hence, feedback and openness are the key for a stable and successful system development. This is not only needed only in the space vehicle system building, but also is needed in the work we do. Thus, no matter how complex a system becomes, the need for effective communication and collaboration among the different designers working at all levels of abstraction will play a dominant role in the success of the product, and it clearly ensures one important point, that there is no single point of failure. Thank you.